A high frequency regime is where the wavelengths become extremely short compared to the dimension of interest. So, asymptotic and approximate methods serve the design needs for high frequencies. When science and technology call for solution for more complex problem, then theoretical models need to be performed with the help of perturbation or asymptotic method. In asymptotic method, the wavelength is usually used as a small parameters for perturbation expansion, and this is the field of physical optics, geometrical theory of diffraction, and so on. A solution is usually ansatz-based. So, for example, when the frequency is high or the wavelength is short, the wave number, which is 2 pi over lambda, is large. So the scattering solution for complex object may assume to be dominated by few prominent features as a consequence of scattering, reflection, and diffraction. The approximate solution may be superposition of solutions where the constants are obtained by matching solution with canonical solution, such as Sommerfeld half-plane solution and Mie-series solution after Watson transformation. In the high-frequency regime, the wave solution becomes plane wave-like. Oh, plane wave behaved like rays, and even though the electromagnetic field is still described by the wave equation, which is hyperbolic type, the asymptotic method with a short wavelengths as a small parameter can be used to extract the prominent features of the solution. So alternatively, we can think of rays as being particle, and this is what happens to light rays. Consequently, this so-called light rays can be described by the transport equation in E-canal equation. So these equations can be derived from a wave equation under high frequency and short wavelength approximation. So high frequency regime also allows for the beamforming of electromagnetic wave, and for instance, in the case of optics, the electromagnetic fields can be focused, and antennas with high derivatives such as reflector antenna can be designed at microwave frequency. Low frequency such an antenna has to be unusually large to increase electromagnetic wave directly. In addition, to this properties, one has to be also mindful of another regime when the frequency is high. So quantum of electromagnetic energy is proportional to the product of Planck constant and frequency. And if this product is not small, we then have a quantum regime. So in this regime, electromagnetic has to be described by quantum physics. And the electromagnetic field, which is observable, is a quantum operator analog. This is a property not derivable from the wave equation, but is a result of quantum nature of light. So hence, when light waves interact with matter in the optical regime, it is essential to consider quantum mechanics to fully model its physical properties. And because of small value of Planck constant, the quantization of electromagnetic energy is unimportant unless the frequency is very high and we operate in the optical frequencies. And because of the quantization of electromagnetic energy, light waves interact more strongly with matter, giving rise to a large variety of physical phenomena. which is nonlinear phenomena, for example. Now I would like to sum up the preceding discussion, and one way to categorize a numerical method is to determine whether a specific numerical method targets large, mid-wave, or high-frequency regime. So both integral and differential equation methods are plagued with instabilities, and when a frequency is extremely low or the wavelength is very long compared to the structure being probed, then this property become more pronounced. So this is because we switch from the regime of wave physics to the regime of circuit physics. This transition indicates change in the solution method when one goes into the low frequency regime. So in the low and mid frequency method, the device we model is about the order of the wavelength, and that's actually what we are mainly going to concentrate on here. So these methods are often considered the most difficult to model because it's challenging to accurately account for polarization, and we really need to obtain rigorous solution to Maxwell equation here. As we know, Maxwell equation govern all electromagnetics, and at this scale, we really have to implement a high accuracy. And in the case of high frequency method, the device we model is enormous compared to the wavelengths, and there are a lot of approximation that you can make. For instance, this happen when lens, if you wear glasses. It's the property of the high frequency case. The wavelength of light is so small compared to the lens that structure properties such as polarization and other become much less important. In fact, light and radio waves and even sound waves are really behave the same way at that point in the high frequency regime. So while approximate method serve the design needs of high frequency, they become less reliable when frequency is low or when the wavelength is long. So one good example is the scattering from aircraft by megahertz electromagnetic waves, where the wave is not short enough to allow for short wavelength approximation. In this regime, computational method in electromagnetic are more reliable than approximate method. And in this class, we are going to concentrate on low frequency method, and we are, for the most part, going to obtain rigorous solution to Maxwell's equation. So the solution are rigorous in the sense that no approximation is built into the method formulation. And physics of electromagnetic field changes as frequency changes, so we consider field as static at near zero frequency, and high frequency are often considered as optical range. So electromagnetics is described by fields, and the field is a function of 3D space and time coordinate system. So this field satisfy the respective special differential equations that govern their physics. So, and electromagnetic physics changes depending on the regime. A gradual process of transformation of the physics and electromagnetics can be easily understood from the simple concept where we compare derivatives with respect to each quantity. So special differential equations that governs electromagnetics have many derivative operators in them. Depending on the regime of physics, different parts of the special derivative operator become essential. The another important concept is that of the boundary condition. So the boundary condition dictates how field behaves around the object, and one can say that field has to convert around the object to satisfy the boundary condition. And because of this, the variation of the field around the object is primarily determined by the object geometrical shape. So much physics and electromagnetics can be understood by the boundary condition and the comparison of derivatives. So because of the boundary condition shapes in the field, the derivative of the field is inversely proportional to the size of the object. And if the typical size of the object is of length L, then the derivative over x is of the order of 1 over L, and the second derivative is of the second derivative over x is of the order of 1 over L square. So from this, one can see that this space derivative, the field is particularly large around small elements of the structure under consideration. And because Maxwell equation contain primarily first derivative in space and time, comparison of the importance for these derivatives that describe different regimes in electromagnetics. So for time harmonic field with angular frequency omega, we can define an associated plane wave with this wavelength lambda, where we can say that c over lambda is omega divided by 2 pi. So consequently, a time derivative we have in Maxwell equation is of the order of omega, and in other words, it's inversely proportional to lambda. And in comparison to the time derivative, which is proportional to 1 over lambda, to the space derivative, which is proportional 1 over L, we find different electromagnetic regimes. So consequently, electromagnetic physics can be divided into the following three types. For low frequency regime is when characteristic size is much less than the lambda, the wavelength, and when the object size is much less than the wavelength, the physics of the field around it is dominated by the fact that time derivative is important compared to the space derivative. So the field physics is close to that of the static field. So second, in this mid-frequency regime that we discussed, is when characteristic size is comparable to the wavelength. In this case, the space derivative is equally important compared to the time derivative, but the size of the object and boundary condition still controls the nature of the solution. And finally, the third high frequency regime is when the size is much larger than the wavelength, and in the high frequency regime, the boundary condition plays less role than the equation in shaping the solution. So the solution resembles a homogeneous solution of electromagnetic equation to plane wave, and plane wave are mathematically represented by rays, can be considered as rays, and rays physics become more important in this regime. And also, in addition to this classification, where we assume that the point of observation is the same order as the size of the object L, but we can also consider other situations. So if one were observe a field at different distances from the object, then physics of the field changes according to this dependence. So we have three regimes. The first is a near field, which occurs when the distance from the object is much smaller than the wavelength. In the mid-field regime, the distance is comparable to the wavelength. And finally, in the far-field regime, the distance is much larger than the wavelength. So in the near-field regime, electrostatic physics is important, and in the mid-field regime, wave physics is important. While in the far-field regime, ray physics is important. And we also can keep in mind that in optics, the ray physics regime can be further refined into a Fresnel zone and Fraunhofer zone.